this part of it. We talked about what a tangent line is. In geometry, the line that is tangent touches this half circle at only one point. At the point that it touches it, it indicates what direction that the circle is moving. If a point keeps moving, then that tangent line is going to change. The slope of that tangent line will change, which means the rate of change of the function will change. So we're going to try to refine what we're talking about, a tangent line here. And this is the part that I wanted to be sure you understand and that you would have an option to ask questions while we're talking about it. So the line here at P1 is a tangent line. The line at P3 is a tangent line because they only touch this curve in one point. They touch it and move off. The line at P2 is not a tangent line. Even though it only touches the curve in one place, it doesn't touch the curve and move on. It doesn't indicate the slope of the curve at that point because it's actually cutting through the curve. And the point of a tangent line isn't that it cuts through the curve and goes, it doesn't bisect it, which means it actually cuts through it. It only touches it and moves on. And that's the same thing that happens at P5. It's actually cutting through. The place where we get in trouble is when we start looking at P4. Because in P4, it does satisfy the idea that it's indicating the direction of the curve. Essentially, you would say it's parallel for a really short time to the curve, except that it does touch it in one point. But unfortunately, it also does bisect the curve because it starts on one side of it and comes out on the other. And a tangent line has to stay all on one side of the curve. We also talked about a secant line. And we talked about defining the slope of a secant line with the slope formula. But what we do is we let the tangent line actually approach, or the secant line actually approach being a tangent line by taking this point and sliding it closer and closer and closer to the other point so that it actually touches in one point. And that's what we did last time. And we did it for specific points. We had numerical values. So the takeaway on this is that what we're trying to do, and I'm going to skip over some of this, what we're trying to do is we're trying to use the idea of a slope, which is an average rate of change, but if we slide the points for the average rate of change so close together that we almost can't distinguish the difference between them, the slope of that secant line becomes very, very close to the slope of a tangent line. And that's important because the slope of a tangent line is actually the same as the slope of the curve at that point. Okay? And that's where the idea of a derivative comes in, because this is your new vocabulary word. A derivative at a point on a curve is the slope of that curve at that point. The way that we find the derivative is we actually slide the 2 points of a secant line closer and closer and closer together until they become as close as we can get to a tangent line. And it's that process that lets us find a derivative. So a rate of change is the same thing as a slope, is the same thing as a derivative if we're talking about those three things at one single point. And this is what we worked on up to this point. But the thing here is that if we had 1 point, we plugged in and we did some arithmetic. And we let h approach 0. We're going to do something similar here, except rather than have to come up with, for every single number we would want to find a slope of a tangent line for, we're going to come up with a formula that lets us find the slope of that tangent line at any value of x. That's where we're headed now. And this is our first example, and at this point I'm going to kind of switch over and work through this one with you. we'll use the calculator for help. Because we are gonna be doing some arithmetic, but not a whole lot, but we're also gonna learn how to use the calculator to help us with this whole finding a tangent line slope thing. There's some built-in features that we haven't learned yet.